Okay, recording has started. So first subject is quasi one-dimensional flow. I will start the video.
So coming to quasi 1D flow, as we talked in the class, this is very important in terms of many different aerospace applications for basically for nozzle.
Okay, I just stopped the video. Can you guys all hear and see the video?
Yes, hocam.
Okay. During the course material, if you don't want to wait until the end of the video, please stop, and you can always stop and ask questions, okay? Just let me know.
Design in different propulsion systems like rocket engines and other turbo engines, turbojets. So this information that we're going to learn today is critical. So basically, just a second. Yes. So basically, we talked about the conservation equations for the 1D steady implicit adiabatic flow. First of all, if you remember, we talked about this geometry, the one on the left, which is basically, just a second, let me get my pointer again. Yeah, so the geometry on the left is basically a constant area duct flow. The flow parameters are changing. They're functions of x. They're only changing along x, so that's why we call it one-dimensional flow. But the area does not change. The area is constant. So compared to this, the one on the right-hand side, in addition to the fact that flow parameters are changing along x, we also allow the area to change along x. So the area varies like x with x, and like seen in this sketch on the right. So this type of flow with one-dimensional variation of flow parameters plus the variation of area along the same dimension is called a quasi 1D flow. So first off, we did this in the class, the control volume analysis of such a flow. So we have our control volume selected like this. So we have the inlet station 1 and exit station 2, and we have the control surfaces at the top and the bottom. And here, if we write the continuity equation, yes, we see that rho UA is constant from inlet to exit. That does not change. If we write the momentum equation, in the momentum equation, the incoming momentum versus the exit momentum, so rho U square A, rho 1 U1 square versus rho 2 U2 square A2, if they are not the same, if there is a momentum imbalance, that has to be balanced by forces. So that's the second law of motion, Newton's second law of motion, right? So basically, that has to be balanced by pressure forces in this case. So the pressure force on surface 1, on this surface at station 1, inlet surface, and the pressure force on the exit surface at station 2, which is P1A1 and P2A2. Now plus we should have an additional term, which is basically the pressure due to the pressure variation of the side surfaces. So that has to be integrated from A1 to A2, which we see in this slide. So if you organize the momentum equation, we have all these terms, and we have the variation of we have the pressure force term due to the area variation from 1 to 2. Now, regarding the energy equation, if you write the energy equation, it has to be energy conservation, means the incoming internal plus kinetic energy has to be conserved, meaning if there is an energy imbalance when we compare the exit to the inlet, that has to be balanced by pressure work. So at the end, in the class also we derived that means the stagnation enthalpy, which is H1 plus V1 square over 2 station 1, has to be equal to stagnation enthalpy H2 plus V2 square over 2 at station.
Question?
Yes, there's an integral equation, integral part of the first equation between A2 to A1.
Yeah.
Is this the contribution from the control surfaces or something else?
Yes. Let me quickly revise that. first go back here. So as you can see, when we talk about 1D flow, this is this type of flow, the cylinder on the left, right? So we have only parameters changing along one direction, along x, and not area is constant. The one that we are interested in aerospace engineering in internal flow problems is more like a what we call a quasi 1D flow, more like the one on the right hand side. So in this case, everything, all the flow parameters are changing along x, again along only one single dimension, but area is also changing. Let me first make that point clear. Now they're coming to your question, the integrals, when we do a control volume analysis, actually. This integral, for example, in the momentum equation, when we are taking the integral, we have, yes, on surface 1 on the left and on surface 2 on the left, we have incoming momentum, outgoing momentum, and pressure forces acting on those. But we do have, if we have a duct that has varying area, on the side surfaces, we do have pressure acting on them as well, right? So because of that effect, the pressure basically acting on the side surfaces, there's no momentum coming in or out from the side surfaces, but there's pressure acting on the side surfaces. That needs to go into the momentum balance as well. So that's why we have this A1 to A2 PDA term. Was this your question?
Yes hocam. Teşekkür ederim.
Okay, good. So I will continue.
If you write the energy equation, it has to be energy conservation, means the incoming internal plus kinetic energy has to be conserved, meaning if there is an energy imbalance when we compare the exit to the inlet, that has to be balanced by pressure work. So at the end, in the class also we derived that means the stagnation enthalpy, which is H1 plus V1 square over 2 at station 1, has to be equal to the stagnation enthalpy H2 plus V2 square over 2 at station 2. So H01 is equal to H02. That's what we mean. Of course, this can only be true if this is an adiabatic process, no heat transfer, and there's no work done on the fluid or by the fluid. This equation is actually discussed a little bit more in the following slides.
Let me make a quick explanation again regarding your question. The one on the integral on the right hand side of this equation is what we call pressure work, right? Pressure work. And that pressure work, when combined with the internal energy, is actually what we know as enthalpy. So this E on the left-hand side of the equation, when combined with the pressure work, actually becomes the H in this bottom equation, okay? The enthalpy. So the final energy conservation equation is, as a summary, stagnation enthalpy does not change. As indicated in the video, if there's no heat transfer or work done on the fluid or so. So this is the conservation of energy equation.
Hocam, was this process is isentropic or not?
In this case, yes. First of all, there's no heat transfer, and we are assuming inviscid flow. So there are no boundary layers or anything on the internal surfaces. So in this case, inviscid flow assumption plus adiabaticity makes it basically an isentropic flow, yes. Okay, let's continue.
Done on the fluid or by the fluid. This equation is actually discussed a little bit more in the following slides. Starting from the energy equation, I can pass one more slide. So here, if we reorganize the energy equation, we have this equation at the top, and if we divide it by ρ1, u1, a1, the left-hand side, and the right-hand side by ρ2, u2, a2, we get this equation that you see here. So P over ρ plus E plus kinetic energy basically is constant along a streamline. That's what it means. So, of course, P over ρ plus E is what we know and define as enthalpy before. So this therefore becomes h plus u square over 2 is constant along a streamline. So if we apply the similar control volume analysis now to an infinitesimal section of the duct where we have area change. So we have station 1 and 2. Now the length is dx. We have incoming flow properties and outgoing flow properties. Only changes are infinitesimal in all flow parameters. And if we write the energy equation, the continuity equation, now it says, yes, differential of rho UA must be equal to 0. And in terms of energy, we have to say dH plus U du is equal to 0. And in terms of momentum, if we do the same exercise, of course, when we do the same exercise in the equation, we end up with many higher order differential terms, such as, for example, here we have dP times du times du. We ignore all these terms at the end, and also we apply the continuity equation. At the end, we reach a very simple equation that basically gives us conservation of momentum for this infinitesimal control volume with area change. Now this is important. Why? Now first of all, I will come back to that in a second, but if our main conservation of mass equation can be written also in this form, d rho over rho plus du over u plus d over a is equal to 0. Now dp over rho, what I want to find is a relation between area and velocity. So this is what basically the title, area velocity relation. So I want to express the rho over rho in terms of those quantities. So in order to go there, I need an expression for dp over rho, which I can write dp over d rho times d rho over rho. But this is also equal to, from the previous slide, if I go back, I have an expression for dp over rho, which is equal to minus u times du. I want to make use of that. So this basically becomes equal to dp over d rho times d rho over rho is equal to minus u du times dp over d rho. But for a flow with no shock waves and with isentropic conditions, we know that dp over d rho is actually for constant entropy is equal to the square of speed of sound. We have seen this before in our classes previously in the semester. So a square, so d rho over rho therefore becomes equal to minus u du over a square, which can be rewritten as minus mach square or times du over u. And therefore we end up with we insert this term into the equation up here. We replace the rho over rho. We have now minus mach square du over u plus du over u plus the a over a is equal to 0. If we rearrange this equation to keep the a over a on the left hand side, we reach this very important equation in compressible aerodynamics, which is the a over a is equal to m square minus 1 times du over u. This is what we know as the area velocity relation for compressible flows. The importance of this is explained. I will try to explain it in this slide. So the area velocity relation basically gives a very important, tells us a very important story about the main characteristic difference between subsonic and supersonic flows. So if the flow is subsonic, so Mach number is less than 1, basically if Mach number is less than 1, you can see that in this equation, this term is going to be a negative term. So there's going to be a minus sign in front of du over u, which means that if there is, for example, a positive change in area, if dA is positive, which means area is increasing along the flow direction, that has to be equal to minus du. So it means that the velocity change must be decreasing. So an area increase comes in with causes a velocity decrease in subsonic flows, which we have learned previously in incompressible flow classes. So u is inversely proportional to a. So as you can see in the sketch, an area decrease means velocity increasing, and an area increase means velocity decreasing. So they are inversely proportional. However, the story is completely the opposite if it's a supersonic flow. If Mach number is greater than 1, Now this term now is positive. So this means that if the incoming flow is supersonic, a positive area change, meaning area increase, means also a positive du, which means velocity will increase. So as presented in the sketch here, area increasing, we have velocity increasing, and area decreasing, we have velocity also decreasing. So this happens in supersonic flows, and it's the complete opposite behavior than subsonic flows. So if you remember, we also in our face-to-face classes we have related this to the existence of shock waves. When we were discussing in Anderson group, the flow turns towards itself, which actually means if you consider the far away streamline, it actually causes an area decrease, and for a supersonic flow that means deceleration, so it can only happen through a shock wave. So our final slide.
Let me explain this point, because we discussed this point also this year. Regarding this area velocity relation, as explained in the video, if you remember when we were talking about oblique shock waves and expansion waves last week, for example, we said when there's a ramp, when the ramp is turning into the flow, that creates an oblique shock wave. And I explained this phenomena such as basically what's happening is if you consider a streamline that is far away from the body, let's say undisturbed streamline which is straight, what happens is the streamline up above is straight, but the ramp is the solid boundary is not straight. There's a ramp. Basically, the turning of the ramp changes the area squeezed in between the faraway streamline and the solid body. A ramp moving up basically reduces the area. So that area reduction, and since we are dealing with supersonic flows, area reduction must cause a reduction also in velocity. Regarding considering this area velocity relation here, since the information propagation cannot be done because the flow field is supersonic, that must happen instantaneously. So that sudden area reduction causes sudden area change can only happen through a shock wave. So that's why we end up a shock wave when there's a ramp moving into the flow. The opposite is true also. If the ramp, if that kind of ramp is moving away from the flow, like in an generating like expansion waves, in that case, what happens is basically the incoming flow is supersonic. Again, considering our far away boundary like a straight streamline, far away from the body. At the corner, when the flow sees a ramp, it suddenly sees an increase in area. And the incoming flow is supersonic. Again, now due to this area velocity relation that we are seeing right now, that must cause an increase also in velocity, also in Mach number. So this whether in the external flows also. So what we are learning right now is what we discussed today is for internal flows, but for external flows also this subject is relevant, and this area velocity relation is valid, and it actually determines whether there's going to be an oblique shock wave or an expansion wave also in the external flows.
And for a supersonic flow, that means deceleration, so it can only happen through a shock wave. So our final slide here, we have basically the main application of this physical phenomena. Basically, we use them in what we call converging diverging nozzles. Here you see the converging diverging nozzle geometry. So we have a high area, minimum area, and an increasing area again. So if a subsonic flow is incoming here, it can, if the certain conditions are satisfied, which we'll see those conditions later, it will reach the Mach 1 condition at the minimum area location, which we call the throat, and then accelerate because the area is increasing, so it will accelerate and go to supersonic speeds. When Mach number is 1 at the minimum area location, we call that the flow is choked. So the opposite behavior also happens if we have the same geometry but incoming flow is supersonic. Then the area is decreasing, so the flow will have to decelerate to Mach 1, decelerate down to Mach 1, and then further increase in area will cause a further deceleration to low subsonic speeds. So again, we have the throat location and the Mach number reaches 1 at the throat location. This is what we call a supersonic diffuser. So these are direct applications of this area velocity relation in compressible flows for quasi 1D compressible aerodynamics. So this ends the session on this topic.
Okay, so we finished our first video as an introduction of basically a compressible flow within a duct in an internal flow problem. And now we saw the area velocity relation. And now the next video is basically the continuation of this regarding converging, diverging nozzle applications that are very much relevant to rocket nozzle design and everything. We will see in the next video. Do you have any questions regarding this first video? We have already discussed some points, but do you have any further questions? Okay, you can always stop and ask. So if not, I will continue with the second video. Okay, just give me a second. Okay, now I'm going to start the second video, which is about nozzle applications and also about what we call area Mach number relation. Again, in internal internal flows, duct flow, compressible aerodynamics. Okay, so this class is about converging, diverging nozzle flows. And so we will talk about the flow physics, related equations of converging, diverging nozzle flows, which are frequently used in different applications in aerospace engineering. So here, when we say a converging, diverging nozzle flow, we are basically referring to more or less a geometry like this. So we have the flow comes from left to right and starts with a region where it's where it's basically subsonic with some certain inlet conditions, stagnation pressure and temperature, and then reaches in the minimum area location the sonic Mach number, and then after the sonic Mach number reaches supersonic flow conditions. So we are basically talking about this internal flow problem. Yeah.
Hocam kusura bakmayın.
Are used in rocket
Evet, dinliyorum. Ya sesi açılabiliyor mu acaba videonun? Çok kısık geliyor da şu an.
Kısık mı geliyor? Doğru, açılabiliyor. Evet. Şöyle bir deneyelim. Bir bana tekrar bakıp söyler misin?
Tamamdır.
Supersonic wind tunnels. Wherever we want supersonic exit flow. So if we have a nozzle flow like this, we are trying to achieve a supersonic exit flow.
Hocam şu an güzel.
Çok iyi. Tamam. Teşekkür ederim. Application, we have to use a converging, diverging nozzle.
And these applications can be, as I told you, it could be rocket engine nozzles, rocket engines, and also it could be supersonic wind tunnels. In the supersonic wind tunnels, in the test section, we of course need a supersonic uniform stream. So therefore, in order to achieve that before the test section, we need to put a converging diverging nozzle. Now, when I say a converging diverging nozzle, here it has two parts, this geometry. So the first part until the minimum area location, by the way, so let's mark this first. This is the minimum area location, and we call it the throat location, throat. And therefore, the first part is the converging part before the throat, and after the throat we have the diverging part. Okay, so that's why we call it converging diverging nozzle. Now, first we will talk about some equations that basically that can be used, the fundamental equation that can be used to design or obtain the first, let's say, design for a converging diverging nozzle flow. So in order to do that, that relation is called the area Mach number relation, and in order to achieve that, we start with continuity equation. So at throat, when Mach number is equal to 1, when it reaches 1, of course the area of the throat, this is a geometry, it has a certain minimum area, so many square meters, but when inside flow, the internal flow reaches Mach 1 at the minimum area location, the flow conditions is such that at the minimum area location, this area actually becomes equal to the A star value that we use in compressible aerodynamics, and the velocity there becomes equal to the small a star, the speed of sound value. So keeping these in mind, we can write the continuity equation such that the mass flow rate rho star u star times a star that's going through the throat must exit from the exit plane. So by the way, let's mark this as the exit plane. Yeah. So we will come back to this subscript as subscript E later, but the mass flow rate going through the throat must be equal to rho times u times a at the exit. Okay, so we can rearrange this equation. We can rearrange this equation to take this a over a star ratio to the left hand side, and then this becomes equal to basically rho star times u star divided by rho times u. Okay, and we can work on this equation a little bit, and which to make it look like rho star over rho 0 stagnation density times rho 0 over rho, so stagnation to static density ratio, times u star over u. Now here u star is equal to a star. Okay, so the thing is, why did we want to do this? Because each of these terms, each of these three terms can be written as functions of Mach number only. Okay, so if we find these functions, put them into this equation, then we will have an equation relating a over a star variation or ratio that's going to be only a function of Mach number. So that's what we're going to do. So let's get a new page. Now for in here, if we start, first let me start with the second term. So this is, we are talking about the rho 0 over rho equation. You know that this is equal to 1 plus gamma minus 1 over 2 m square to the power 1 over gamma minus 1. This is from the isentropic relations. Now when rho, the static density, is equal to rho star, then of course Mach number equals to becomes equal to 1, and then this rho star over rho 0 becomes now only a function of gamma, not a function of Mach number anymore. So it becomes equal to 2 over gamma plus 1 to the power 1 over gamma minus 1. Okay. So yeah, so we have basically obtained, we have now two relations for rho 0 over rho and for rho star over rho 0, which are only either functions of gamma or functions of Mach number. And the last one is the relation that that's a star over u, or we can write it as u over a star. Well, this u over a star is actually what we defined previously in our face-to-face classes as m star. So in if we take the square of it, we have the m star square, which is a function of only flow Mach number, which we have derived previously also. So this is equal to gamma plus 1 over 2 m square, 1 plus gamma minus 1 over 2 m square. So we have also derived this before. So now we have three relations for
Hocam hazır buradayken bir şey sorabilir miyim?
rho.
Tabii dinliyorum.
What's the difference between M star and M? Actually, I think it's the same thing because the relative velocity over speed of sound.
This is a very fundamental question. You need to go refresh the video because we discussed this a lot in the class.
Yes, yes, hocam. I was already asking to you, but
let me refresh your memory. Okay, M star is defined as like this: u over a star. So when we are talking about, let's think about a streamline, right? A streamline. So anywhere on the streamline, you will have a u value, some velocity, right? And what is a star? The question is, what is a star? A star is not the local speed of sound at that location where you, for example, get the u value. A star is a location on the same streamline, okay, where you reach, for example, Mach 1 condition. So at that condition, on that location where you reach Mach equal to 1, there will be a certain static temperature level, T star, right? So at that T star level, that will correspond to an A star value. So when you compare your local velocity to the speed of sound somewhere on the streamline where it actually reaches Mach 1, we define this one as M star. Okay?
I got it. I didn't know about the difference between A star and A. Thank you.
Yes, okay. We discussed this a lot. So if you want, it's in one of the previous videos in this semester. I mean, we discussed it. You can refresh your memory also by watching that. Okay. Okay, good. Let's continue.
Star over rho 0 and basically u over a star, so that we can plug them in all into the equation for a or a star above. So substituting these into the a over a star equation, okay, we get a relation which looks like this. So a over a star square, okay, becomes equal to, the first term is rho star over rho 0, so 2 over gamma plus 1 to the power 2 over gamma minus 1. That's the first term. The second term is rho 0 over rho, so we will directly write this expression from above, 1 plus gamma minus 1 over 2m square, yeah, and 2 over gamma minus 1. And finally, we have the relation for a star over u. So we have u over a star over there, so we will just write its inverse. So it's going to be equal to 1 plus gamma minus 1 over 2m square divided by gamma plus 1 over 2m square.
So now we do have a relation for A over A star square in reality as a function of either gamma or Mach number. Nothing else shows up on the right hand side. So let's get a clean page. Yeah, and just organizing this equation a little bit more to look a little bit in a simplified manner. We have this equation A over A star square now equal to 1 over Mach square bracket 2 over gamma plus 1 plus gamma minus 1 over 2 m square, okay, and to the power gamma plus 1 over gamma minus 1. So let's mark this equation here. So this relation is known as the area Mach number relation in compressible aerodynamics for, let's say, internal flows for converging diverging nozzles. So this is known as the area Mach number relation. Okay. Now this relation is interesting, and it is, let's say, the first step that we can use when we are designing, when we want to design a converging diverging nozzle for our any application that we need to do it for. For example, this relation first of all tells you that when we are talking about this converging diverging nozzle shape, right? So let's say flow is coming from left to right, and we have this is our x-axis direction. So at any location, basically, area is a function of x. So if you are interested in finding this, and let's say there is a minimum area location, a T throat area. Now, if you want to design a nozzle such that it will be choked, it will be we will come to choking in a little while. But at the minimum area location, if you want to reach Mach 1, then that A throat will become A star. So this AX distribution is going to be entirely only a function of Mach number distribution. So in order to find the shape of your nozzle, you need to you need to know the Mach number distribution. So if you have a subsonic Mach number distribution here, Mach number equal to a subsonic Mach number distribution here, and sonic Mach number here, and some supersonic Mach number distribution here, that basically sets your geometry. This also works the other way around. So Mach number implicitly from the equation above is a function of A over A star. So if you have, let's say, manufactured a geometry, this is fixed, A over A star is known, then that automatically sets your Mach number distribution. So therefore, this is the main reason why the area Mach number relation is extremely useful in designing converging diverging nozzles for rocket engines or for supersonic wind tunnels. Okay, let me make one more comment regarding this area Mach number relation. For example, the thing is, regarding the design of such a geometry, meaning a converging diverging nozzle geometry, for example, if you know your inlet Mach number, so let's say at the left hand side it's coming in subsonic, so you do have an inlet Mach number, you plug that inlet Mach number into this equation, and it will give you an A over A star value, meaning that if in order to reach choked flow conditions at the minimum area location of this nozzle, your initial area, which is the left hand side inlet area, to the minimum area ratio must be equal to that number for that given to that numerical value for that given Mach number. That's what it means. Okay, if that ratio is not equal to that, with that given incoming inflow Mach number, you will not be able to choke the flow at the minimum area location. Why is choking important? And what is the physics relevant to it? We will actually see in the next few videos. But and I must say, it is the phenomenon of choking is one of the most important phenomena in compressible aerodynamics, especially in internal flow of compressible supersonic, or in general, let's say, compressible aerodynamics. We will talk about it. But so therefore, we need to know what kind of area ratio that we will have to choke the flow at the minimum area location. One example, let me give you one quick example regarding an application for this point, and then we will give a break. The application is, for example, at the, I don't know if you ever noticed, but for example, for fighter aircraft, at the nozzles of fighter aircraft can actually change shapes. They can actually reduce the exit area, and I mean they can actually control the exit area. Sometimes they reduce it, sometimes they increase it. So that is entirely the controller system of the engine, which is connected to the controller of the aircraft. What it's doing is entirely making use of this area Mach number relation. And to keep the performance of the aircraft and performance of the engine at the required condition, depending on the flight condition, the nozzle exit area is manipulated. And in most, let's say, most of the fighter aircraft engines, most of the engines are equipped with what we call only a converging nozzle. So there's no diverging part. There's only the left-hand side part. It comes in from a large area, and it basically gets into a minimum area location, and that's it. That only has the converging part, and the minimum area, amount of minimum area is controlled. So depending on the conditions inside the engine and depending on the flight conditions, the minimum area is changed to always keep the operation of the engine at maximum performance. The thing is, the flight control system knows how to change that geometry through usage of the area Mach number relation, which is already programmed into the flight controller and the engine controller of the aircraft. Okay, so this is another usage, but we will see, we will actually discuss more starting from this point. So at this stage, we only finished 2 videos. We have actually 3 more. But okay, let's give a break and then we will continue with this topic. Okay.
Hocam,
Mm-hmm.
How do you decide on the length of subsonic part and supersonic part?
The length is not that relevant, but in the first in this stage, okay. The important thing is area variation, because we are dealing with quasi one-dimensional flow, but of course the length is related to the shape of the nozzle. As you see, it does have some kind of a curved shape. So this curved shape is also important, but especially in the diverging part. In the converging part, it is not that critical, but in the diverging part, in the right-hand side part, it is critical, that bell-shaped geometry. And I mean, there are certain, let's say, supersonic aerodynamics methodologies that we use to design that shape, and that determines the length of the divergent part. The length of the converging part, if it's accelerating from subsonic, we just need to be careful about some flow separation related issues. But these are our at least in this stage, that are in the context of our current discussion, are secondary concern. Okay.
Teşekkür hocam.
Mm-hmm. Okay, let's give a break and let's meet again at 2:40.
Hocam,
Evet.
bir girip çıkabilir miyim? Bir sıkıntı oldu Zoom'da, acaba sıkıntı olur mu?
Yok, olmaz. Girip çıkabiliriz. Evet. Görüşürüz. Okay, so we will continue with the flow development in converging diverging ducts. And let me share the next video. Okay, let's start. Okay, so in this session now, we will talk about the flow development in converging diverging channels. We talked about the relevant area Mach number relation in another video. And here now we will talk about the flow development. This basically is a converging diverging channel that you are seeing here, as we talked about in the other video, and the flow is coming from left to right, and we will talk about the flow development properties as we go from subsonic to supersonic, and how to achieve fully supersonic flow field in the diverging section. So the flow field, of course, is entirely dominated by the pressure ratio, pressure difference between the inlet and the exit. Now, in addition to this inlet and exit pressures, actually there's also what we call the back pressure. Let's call it PB. So we call it the back pressure. So that's the actual pressure in the environment after the nozzle. Okay, so when the flow is subsonic at the exit, generally all the time PB, back pressure, is equal to the exit pressure. But when the flow is supersonic, the story can be a little different. So we will talk about this. In reality, this back pressure setting controls have a dominance over what kind of flow field we will have inside the converging diverging nozzle. So yes, normally if there is no pressure difference, meaning let's say the static pressure at the inlet is equal, static pressure at the inlet is equal to the static pressure at the exit, of course that means there's not going to be any flow. So zero Mach number everywhere. So we will start from that scenario, and we will do like a hypothetical experiment, and we will start from that condition where exit pressure is equal to the inlet pressure, and then we will keep the inlet pressure the same but start reducing the exit pressure or back pressure slowly. So it will slowly be smaller and smaller and smaller compared to the inlet static pressure. So let's say that we reduced a little bit. So if initially, let's say our P exit to inlet P static, or inlet conditions can be considered as, this chamber, this inlet area can be considered to be connected to a large, let's say, chamber where the flow Mach number is actually zero. So static pressure will be equal to stagnation pressure. So basically, if in that condition, let's say P over P0 is equal to PE over P0, then there will be no flow, zero Mach number. Then let's say we reduce the exit pressure tiny bit. So PE is a little bit less than the inlet static pressure. Then of course, let me try to draw it in that situation. So I have two plots. I will plot the variation of Mach number with respect to x and variation of P over P0 with respect to x, static pressure with respect to stagnation temperature for different scenarios. So x is of course the
the longitudinal direction along the converging diverging duct, right? So basically, in the first case where we have reduced the exit pressure a little bit, the flow there we will generate basically a very low subsonic flow field. There will be a nice breeze going through this converging diverging duct. Mach number will start and accelerate and then reach to a maximum and then decelerate towards the exit. So let's say this is our first scenario where we have PE is a little bit less than the inlet static pressure. So in that condition, corresponding to that condition, let's say, the pressure variation inside the channel or the converging diverging duct, the pressure as we get closer to the minimum area location, the throat location, we will reach to a minimum pressure and then back again to a higher pressure level. Okay, so now we keep doing this experiment, extending this experiment furthermore. So let's say in the second scenario, we decreased the exit pressure even further. So this will result in even in a more accelerated flow. We will reach higher Mach numbers in the minimum area location, and then we will have a deceleration towards the exit. So in the static pressure variation, it will reach to let me try to draw it better. It will reach to lower static pressure values near the minimum area location, the throat location. Let's remove this. Let's try to draw it one more time. So it will reach to, let's say, lower static pressure, then increase again. Yeah. So if we keep doing that, meaning if we keep decreasing the exit pressure further and further, at some point we will reach an exit pressure such that at that exit pressure we will reach sonic conditions, Mach number equal to 1 at the throat. So let's say that's marked here. That's marked here on the plot. This Mach equal to 1 line is here. Of course, when Mach number is equal to 1, from the isentropic relation, let's write it over here, we know that the stagnation pressure to static pressure, or rather, actually, let's write it in the reverse sense because we have the reversed version on our plot. So static pressure to stagnation pressure ratio, we know that is equal to 1 plus gamma minus 1 over 2. So m square to the power minus gamma over gamma minus 1. Okay. So if you insert Mach number equal to 1 here in this equation, so that's basically going to be our sonic condition at the throat. Then assume gamma is equal to 1.4 for air flows, you will end up with this P over P0 ratio as 0.528. So therefore, if we keep reducing our exit pressure, we can reach a condition such that the Mach number again will increase. Sorry for my bad drawing, but reach the sonic condition and then drop down again to these conditions. So we have our second and third scenarios here, and here we have at this point Mach number will be equal to 1 at the throat area, minimum area location, and the static pressure at that condition, it will be equal to let's say it will get reduced, it will reach this specific value, and then it will basically reach to a lower pressure level. By the way, I have to correct this drawing here, right? So let me choose this. Of course, let's make it a little bit more accurate. the pressure levels cannot be the same at the exit, right? Also the Mach numbers. So let's make a little correction here. So of course the pressure in all scenarios, let's say 1, 2, and 3 will be lower and lower, and the Mach numbers will be higher and higher. So let's remove this 1 to another place. Okay, and so Mach number will be higher and higher. Well, it's not going to be 0, so maybe I should correct this as well to not mislead anyone. So let's redraw this little detail one more time. So let's say we'll have a little Mach number here, a little bit more than that, and a little bit more than that at those 3 sections, because we keep reducing basically we keep reducing the exit pressure. So and this is by the way, the first one is this is 1. So well, now we are at scenario 3. We have in scenario 3, in actually all scenarios, we have full subsonic flow everywhere in the nozzle, from in the converging part and in the diverging part, except for scenario 3, we have Mach number equal to 1 at the throat. Otherwise, everywhere in all scenarios up to this point, we have fully subsonic flow. Well, we will go further than that. So the thing is, in the diverging part, as we have discussed in the previous video, that we may want to have fully supersonic flow, right? So in different applications, we have talked about rocket engine nozzles and supersonic wind tunnels. So we may require in different applications fully supersonic flow. The question is, how do we obtain that? Because until this point, we have fully subsonic flow. So of course, you can imagine, in order to achieve higher and higher Mach numbers in the diverging part, we need to reduce the exit pressure or the back pressure furthermore. So let me first put a note here. If let's say 4 exit Mach numbers that are subsonic, okay, the exit pressure will be equal to the back pressure. So exit pressure, when I say exit pressure, is the static pressure right at the exit plane of the converging diverging nozzle, right at the exit plane where we have a jet outgoing. PB is the back pressure that's outside. So that's your environmental condition. That's the static pressure, you know, somewhere here where you would have a chamber, or you could have the whole atmosphere for yourself if you're flying. So for that condition, for ME and exit Mach number, the Mach number at exactly at the exit plane, less than 1, subsonic condition, PE will always be equal to PB. Now, of course, let's keep this as a note here. That's not going to be the same if it's a supersonic exit flow, which we would like to have.
Okay. Any questions regarding this video?
Hocam, can I ask something?
Sure.
In the second graph, we begin from 1 for P over P0 for all scenarios. Why is it like that? I missed something, I think.
It was described partly in the video, but let me explain it a little bit more. At the very left-hand side plane, right? Or on the left-hand side plane where we have the inflow condition, we are assuming that, as I explained in the video, this inlet is connected maybe to a large, very large container, very large chamber, or it could be the inlet of your, for example, combustion chamber in a, it could be the exit of your combustion chamber in your rocket engine just before this nozzle, where indeed Mach numbers are actually very low, maybe not exactly close to zero or exactly zero, but maybe very low. So at those very low Mach numbers, static pressure and stagnation pressure will be very close to each other. So in the current discussion, we are basically idealizing this. We say, okay, this left-hand side of this converging diverging nozzle is connected to like a very large chamber in which we have stagnation conditions. Basically, nothing is moving. So our starting point is basically a Mach 0. So that's why static pressure is equal to stagnation pressure. So it's equal to 1. Okay.
Okay, hocam, thank you.
Any other questions? One thing that I would like to clarify is maybe not clarify, but some further explanation. Actually, I guess it will be explained more in the second video, but this PB and PE business. PE, I will repeat the explanation in the video. PE, P exit, is the static pressure on the exit plane. So through which we have a jet outgoing from the nozzle, right? So on that plane, that static pressure will be related to the fluid motion where you have an exit pressure. PB is not related to the jet. PB is outside, so away from the jet, way back from the jet. It, as it's said in the video, it's probably the atmospheric pressure. It could be the atmospheric pressure if this jet is issuing into an atmosphere, or if it's operating in space, P back pressure will be 0, for example, in that extreme condition. P back is that outside condition, or we can call it P ambient. PE is not that. PE is related to the fluid static pressure at the exit plane, where you have sometimes subsonic, sometimes supersonic, depending on the condition, where you have a fluid flow or gas flow. So, but if exit Mach number is subsonic, this exit pressure is equal to the back pressure. So whatever happens outside in the atmosphere, they must be equalized, because disturbances get propagated with speed of sound, and everything communicates with each other, meaning exit plane communicates with outside and everything. So through pressure waves, so those pressure values always keep equalized. That's not the case if exit Mach number is supersonic, and we will see that in the other video. I just wanted to make this point a little bit more clear. Any other questions regarding this video?
Hocam, am I correct? We demonstrate this situation by keeping the first inlet of this converging diverging nozzle as a stagnation, and I mean the stagnation point, and they're decreasing the back pressure and sucking the air left to right.
Decreasing the exit pressure, not the back pressure. PE, we are decreasing PE. If it's subsonic, they are equal, as I said. But we are effectively, during our hypothetical experiment, we are decreasing PE, P exit.
Okay, sir, thanks.
Mm-hmm. Okay, there will be more explanations. This was just a part 1 of this discussion, as you can see from the title here. Let me share part 2.
So in order to generate this supersonic exit flow, we need to reduce the exit pressure furthermore. Now, the thing is, before we go there, we need to talk about an important point here. When we reach Mach number 1 condition or sonic condition at the throat, so let's write it here. When Mach number reaches 1 at the minimum area location, which we call the throat, then we call this condition
we say the flow is choked. Okay, so say the flow is choked. So basically what happens is when we reach this condition, okay, the flow reached sonic condition. So no matter what you do downstream of this flow field, so flow reached sonic condition here at the minimum area location, and what we want to do further is to reduce the exit pressure more to get to start to generate supersonic flow in the diverging part. But the thing is, if we keep reducing the exit pressure, which is, as you know, it's a kind of disturbance that we are applying, this information will never reach upstream in the to the converging part of the nozzle. You know, we have talked a lot about this in this class. The information in a compressible flow environment is propagated through sound, it's propagated propagated with the speed of sound. So any disturbance that we create at the exit, like reducing the exit pressure, will propagate upstream with the speed of sound. However, it cannot pass the throat location where the flow is oncoming towards this exit with the speed of sound, because we reached Mach number 1. So therefore, whatever disturbance that you create at the exit will never reach upstream of this throat once the flow is choked at the throat location. That's very important characteristics of converging diverging nozzles. As soon as we reach Mach number 1 condition at the throat minimum area location, then the flow upstream of this, so in the converging part, is basically frozen. That will not be affected anything that's happening downstream in the diverging part once the flow is choked. So when Mach number is equal to 1 at the throat. And of course it cannot increase even more. The maximum Mach number in the minimum area location that you can reach is Mach number equal to 1. So it will stay the same, and all the upstream flow will stay the same in the converging part. Nothing will change. There will be some subsonic flow in the upstream part. It will accelerate to Mach 1. It will basically, everything will stay the same. All the changes after this point will happen in the downstream part, in the diverging part. So I just want to quickly draw here. So this actually sets also, before we go further discussing the Mach number, this also sets a condition on our mass flow rate that can, or the, let's say, a amount of maximum mass flow rate that can actually pass through a converging diverging nozzle. So as soon as you reach Mach 1 condition, you have reached the maximum mass flow rate condition, and you cannot increase the mass flow rate going through this nozzle with a given geometry further. It's fixed. So anything that you do at the exit to increase, let's say, to increase the mass flow rate will not work, and you have reached the maximum mass flow rate condition. In fact, there is a plot about this. Let me try to show you here the maximum mass flow rate plot. So use this little area down here. Okay, so let's say this is the mass flow rate, and the y-axis is the mass flow rate, and it will show a pattern like this. Basically, it will stay constant. Okay, and it will go to 0. So meaning that 0 is of course no flow condition, where exit pressure is equal to the inlet pressure. So as you keep reducing the exit pressure, so basically let's say this is P over, we can say P0, and static pressure is equal to stagnation pressure at the inlet. So that's why I wrote that. let's say this is P exit over P0. So this is equal to 1. So when the exit pressure is exit static pressure is equal to the inlet static pressure, then there will be zero mass flow. If you keep as you keep reducing the pressure, okay, so mass flow rate on the y-axis will start increasing. It will increase and increase and increase, and it will reach, you can see here, a maximum value, so m dot max. And then even if you keep decreasing the exit pressure, moving towards left on the x-axis, m dot or mass flow rate will not change. So that happens when basically after choking. Okay, so that's an important physical phenomena as well. So if we keep continuing to our discussion on the flow development after this point. So at this point, at this stage, at the end of scenario 3, we have reached the sonic condition at the throat. But as we said, we require fully supersonic flow at the exit plane. Now, in order to reach that objective, to obtain fully supersonic flow at the diverging part of the nozzle. So when I say diverging part, it's here, right? Just to remind you. So diverging part of the nozzle, we will keep reducing the exit pressure. We will keep reducing the exit pressure. However, that's as we just discussed, it's not going to affect what's happening upstream of the throat. So the Mach number distribution will be the same right on top of scenario 3. So if I draw this case with a red line, I will try to follow the same line, let's say same line here. Will reach sonic condition. Then in some, since the exit pressure is lower now, that we will have some supersonic region within the diverging part of the nozzle, and however, this exit pressure is still it's still high, meaning that in order to obtain fully supersonic flow in the diverging part, in this part, if we want to obtain fully supersonic flow in the entire diverging part, that can only happen at one specific exit pressure. So if this exit pressure that we just lowered from scenario 3 is higher than this required exit pressure, required for what? Required to obtain fully supersonic flow in the diverging part, then what will happen is, if the exit pressure is higher than that, the flow basically will go through a shock wave. There will be a normal shock wave generated at some X location. So there will be a sudden drop in Mach number. Okay, and then in this the Mach number then will continue in such a manner. So basically, this location is the shock wave location. So it will happen somewhere, let's say here. Let's say we will have a shock wave. We try to use a better tool for this to mark the shock wave. Let's say somewhere here. Okay, we will have a shock wave, and let's say this is at location x1. So at this location x1, we will have a shock wave. In terms of pressure, the pressure distribution upstream of the throat again will not change. So I will also try to follow the same line as to the best of my ability. Then pressure will keep dropping, keep dropping, keep getting reduced until x1 location where we have the shock wave. Then there will be a jump, obviously, in the static pressure, and then it will go up as our fourth scenario. Okay. Now,
in this situation, we have, as you can see, we have achieved supersonic flow in some part of the nozzle. So here we have, for example, supersonic flow, but we don't have fully supersonic flow in the entire diverging part. There is still a shock wave. The supersonic flow, when it encounters this shock wave, it will go to subsonic. So the exit basically will be still subsonic. So that's still I haven't reached my objective. So we keep reducing the pressure more. As we keep reducing the exit pressure more and more, basically what will happen is we will be pushing this shock wave towards the exit of the nozzle. So this shock wave, let's say, it's another location. Actually, let's do this. Let's do this. So this shock wave will be moving to the right, towards the exit of the diverging part. So as we keep dropping the exit pressure, it will move further and further downstream, further and further downstream, and at some point, at a certain exit pressure, it will reach the shock wave will be located exactly at the exit plane. Okay, so let's try to mark that condition on the graph. So the flow is choked, so the upstream conditions again will not change. So I'm again trying to follow the same line. Okay, and then basically this line, or this line, eraser, correct this. Yeah. So this line will continue until now the new shock location, which is all the way at the exit, but the shock now at scenario 5 is located right at the exit plane. So the flow will basically be fully supersonic. As you can see, in this region it's fully supersonic, but the exit is still subsonic because it still needs to go through the shock wave. So that's still not good. In terms of pressure, yes, the pressure basically will be reduced further to a level, but there's a shock wave right at the exit. So let's say this is going to be our scenario 5. Okay, exit is still subsonic with high pressure, and there is similar to scenario 4, there is a shock wave. It's not inside the channel, but it's right at the exit plane. So our objective is partly reached, meaning that in the divergent part we do have fully supersonic flow. However, the exit is not supersonic. We also want supersonic exit, because if you remember our previous video, we discussed this, for example, supersonic wind tunnel condition. In the supersonic test section, we require a uniform constant supersonic stream, which can only be created by placing a converging diverging duct before that. So the duct has to deliver a supersonic exit. And similarly, if this is a rocket engine, and if there's a shock wave sitting right at the exit plane, that will first of all cause a big stagnation pressure loss. That's not good for your engine. Plus, if you have low Mach number exiting your rocket, that's not going to create a lot of thrust. So so basically what we want to do is to get rid of this shock wave, and what we do is we basically keep reducing our back pressure even a little bit more to push this shock wave out of the way.
Okay, so in the last sentence, I think I missaid it, reducing the exit pressure, I should have said. But as you see, if we keep reducing, what we are trying to achieve, to summarize in this video, what we're trying to achieve is the fully supersonic condition in the diverging part without any shock wave. Okay, so shock waves, because when we do have shock waves, they cause stagnation pressure loss. And if this is an engine, as I said in the video, it causes thrust reduction, we don't want that. And in supersonic wind tunnels, normally just before upstream of the test section and inside the test section, we want fully supersonic flow. But in order to obtain that just upstream of the test section, just before the test section in the wind tunnel, we generally place a converging diverging duct. So at the exit of the duct should provide fully supersonic flow. So we really do not want this normal shock wave there. So therefore, in order to obtain this shockless, I must say, shockless condition and shockless fully supersonic condition, I must say, that can only be obtained at a specific P exit value, So that was kind of a summary. Right now, that specific P exit value has not been reached in this video. We have reached scenario 5, and scenario 5 still is at that scenario 5. We still have a normal shock wave. Our exit pressure is still not low enough. It's still not low enough so that we can have a shockless, fully supersonic flow. So we will reduce it a little bit more, and then the shock will basically disappear. We will talk about scenario 6, and that will generate basically a fully supersonic flow in the diverging part with no shock waves present. So that's in the next video, part 3. Let me share that with you.
So if we go now in our next scenario, let's call it 6.
Can you see the video?
Yes, sir.
Okay.
We will reduce the back pressure or the exit pressure even more. Then what will happen is, of course, nothing will change in the upstream condition. Nothing will change here. This is frozen. Then downstream condition now we'll reach to basically to a proper exit pressure, okay, such that it will be slightly lower than 5. So let's call it 6. Now it's going to be a much lower pressure, static pressure compared to 5. Okay, you can see that here compared to 5, it's going to be a much lower pressure, and so we will have fully supersonic in the full supersonic flow in the diverging part, and also we have supersonic exit flow. So here exit will be also greater than 1. The static pressure corresponding to this case, also the static pressure will not jump right at the exit. It will actually go down to a slightly less value, let's say 6 here. Okay. If in the condition that we marked as 6, the flow is perfectly uniform, meaning that in that condition, let's mark it here. In that condition, we have subsonic flow in the converging part. The flow is choked, so we have sonic conditions at the throat, and there's no shock wave basically in the diverging part, and the exit is supersonic. Okay, so that's our objective. That's how we. That's basically the development of flow field from subsonic to supersonic in a converging diverging nozzle flow. There are 2 more things that I would like to discuss, and maybe I can use a new page for this. So let's use this empty one. Now let's draw.
Yes.
Should we drop the pressure even further for higher Mach numbers?
Higher Mach numbers where?
higher than 6. Condition 6.
Higher than condition 6. You mean if there is more drop in terms of you want to drop the exit pressure more, it will not change. Okay, because once you reach that exit pressure, the flow is fully supersonic inside the diverging part, right? Right?
Yes.
So now what will happen is any change that you do, or maybe I should say any disturbance that you do at the outlet will never reach anywhere upstream of it, because it's entirely supersonic. The flow is oncoming towards the exit faster than the speed of sound everywhere inside the divergent part, everywhere. So anything that you do at the exit, that information will never reach anywhere upstream. So you can never change it. The nozzle is basically locked aerodynamically.
Okay, thank you, sir.
Mm-hmm. Our condition at 6. So we have the condition that is developed, and we have, let's say, exit, supersonic exit, supersonic diverging part. Delete this. And yeah, we have supersonic diverging part. Yeah, and we have the corresponding pressure distribution somewhere, something like this. Good. So this is, of course, these sketches are just representative. Okay, now when the flow is exiting supersonically, so there is an ME that is greater than 1, exit static pressure doesn't necessarily have to be equal to the back pressure. Okay, so that's different than the case that we have in the subsonic flow. In the subsonic flow, in the previous pages, we have said that yes, for ME is less than 1, PE will always be equal to PB. Now the story is different. When ME is greater than 1, PE can be different than PB. So back pressure outside can be different than the exit of the jet, the static pressure of the jet right at the exit plane. Now, if this happens, there are basically 3 different scenarios that can happen. So the first scenario is if we have what we call an overexpanded jet, meaning that, so I will just draw half of the nozzle, so just the diverging part, because converging part is basically fixed after choking. So let's say in this scenario, we have a jet exit, we have a supersonic jet exiting our nozzle, so M exit is greater than 1, and we have such a case that P exit of this jet is actually lower than the back pressure. Okay, so the jet normally, if it perfectly expands to whatever we have outside back pressure, we call it the perfectly expanded condition. However, right now it's not. We have a jet that has a static pressure at the exit that's lower than the back pressure. Okay, so if this is the case, what happens is, since the jet exit plane static pressure is lower than the back pressure, the flow has to reach the back pressure, because this is that's what we have outside. The flow, the supersonic flow, will have to go through a series of oblique shock waves. So let's say these red lines, there will be like a series of them, and in general they will generate a diamond-like pattern.
So let's say this is our jet boundary, and so these diagonal lines will be our oblique shock waves that will be generated right at the exit plane. Okay, simply because of the fact that our jet exit pressure is expanded than what it should be expanded to. So because of the over expansion, the static pressure dropped more. So in order to reach the higher pressure at the outside in the outside world, it can only reach to these higher pressure levels through existence of shock waves. In fact, these diamond-like shock wave patterns can be observed in different exits of different nozzles, not only rocket engine nozzles, but also turbojet engine nozzles and turbofan engine nozzles for fighter aircraft. So yeah, so this case, let's write it down, is called overexpansion. So this is a overexpanded nozzle, this scenario. Okay. Now, the other way around can also happen, meaning that the exit pressure of the supersonic jet can be higher than the exit pressure. Okay, so let's try to draw the divergent part of the same nozzle.
I mean, exit pressure can be higher than the back pressure.
Now we have again a supersonic jet. So the exit pressure doesn't have to be necessarily equal to back pressure. So we have a supersonic jet exiting, and E is greater than 1, but now PE is greater than P back. Okay. Now this is called under expansion because the flow is not, I mean, ideally we would want it to expand to PB. So we want ideally PE is equal to PB. That's the perfect expansion. However, it's not expect to that level. So it's still higher. But at outside we still have PB. So it has to reduce its static pressure to levels of the level of PB. So when that happens, unlike what happens in the previous overexpansion situation, the flow now will have to go through a series of expansion waves, as we learned as we learned the fundamentals of it in our previous classes. The overexpansion case, so these were, let's write them down. These were oblique shock waves. This is happening outside the nozzle, and these are now for under expansion. These are expansion waves, Prandtl-Meyer expansion waves. That happens again outside the nozzle, but the supersonic flow stream will have to go through these expansion waves. And this case here, we call this case under expanded nozzle. Okay, under expansion. Okay. Of course, when the ideal case happens, meaning that when we have a perfect expanded nozzle, then the flow, there will not be any shock waves outside, there will not be any expansion waves outside. So in this case, the flow will go through, we will have a nice and uniform stream. Let's do a little sketch over here. So we will have a nice and uniform supersonic stream without any shock waves, without any expansion waves. It's perfect. The PE is perfectly matched to PB. Okay, so we have fully supersonic flow inside the divergent part and fully supersonic flow exiting the nozzle. No shock waves inside or outside, and no expansion waves outside. And this is basically the perfect expansion case. Okay, so now this basically in this video what we have done is we have went through what happens to the flow when it's accelerating, or what happens to the flow of development inside a converging diverging duct, all the way from fully subsonic regime to supersonic regime in the divergent part. And we have discussed the flow physics that's happening and the flow of development that's happening from subsonic to supersonic in a converging, diverging duct.
Okay, let me quickly make one note here. For example, this overexpansion case. I mean, first of all, let me say that when we have a subsonic exit, I said P exit is always equal to PB. When we have a subsonic exit Mach number, so that's for sure. When we have a supersonic exit Mach number, we don't know if it's going to be equal to PB or not. It may be equal. And if it is equal, that's perfect. I mean, we call it perfect expansion. Anyway, I mean, it's the best situation because there will be no shock waves outside or inside. It's a perfectly supersonic jet exiting. So this is one of the possibilities. It can happen. But what can also happen is these two cases when PE is less than PB, which generates, which is called an overexpansion. So over expansion means PE is so low, it's overly expanded, it's so low that it's lower than PB, and it therefore, but outside the nozzle, it still has to reach the atmospheric condition because it is being released to the atmosphere. So only a possibility that it can now increase its static pressure from PE to PB is it has to go through a series of shock waves. And there were some pictures during the video. Let me see if we can see them again. Yeah, here in these pictures, the nozzle of SR-71, for example, these blobs of yellow spots are the diamond shock diamonds. We call them shock diamonds. So these shock diamonds here at the exit are those blobs of yellow regions, and also in the other nozzle of the F-22, for example, you see the same thing here. And generally, for example, this happens when you're launching a rocket from sea level. At sea level, of course, environmental pressure is very high. So generally, nozzles operate in the overexpanded regime. So if you watch videos of, for example, rocket launching from spaceports, rockets launching, and they generally launch from sea level, you can directly see from those videos the shock diamonds are generated. Those are just due to the oblique shock waves. And as you go, let's say you launched your rocket, and as you go up in the atmosphere to higher and higher altitudes, of course, atmospheric pressure outside your rocket very quickly drops. So that PB very quickly drops, and at some point you will end up with the second scenario. The second scenario meaning an underexpanded nozzle operation, where your P exit will be larger than your PB. In that case, again, in some launch videos, you will see, they zoom into the rocket engines to see their performance. And you can see a very wide jet actually exits, very wide supersonic jet exits from the nozzle. And at the very edges, that jet is basically going through Prandtl-Meyer expansion waves. So a space launch operation from sea level to space, during this launch operation, the rocket engine nozzles goes through all these phases. First starts with overexpanded, and then at some point perfectly expanded, and then underexpanded. But for a rocket that is flying more like horizontally, let's say, or a fighter aircraft that's flying horizontally, meaning that at a constant altitude, so at a constant PB level, so depending on the PB level and depending on the nozzle shape, the nozzle could be operating in an overexpanded fashion, or in an underexpanded fashion, or in a perfectly expanded fashion. Okay, so this is a little bit more extra information. Sorry, it's already 3:35, so let's stop here. We will continue with other topics tomorrow. Regarding our compressible flow contents. But with these 5 videos we watched today, we basically close the subject of quasi 1D flow area Mach number relation and the converging diverging nozzle subsonic to supersonic operation. Do you have any other questions? Maybe very quick questions because we are already over time.
Hocam, what is the effect of over expansion and under expansion on the performance?
If it's not a perfectly expanded nozzle, that drops the pressure because if I don't know if you are probably I don't know if you're taking the propulsion class this semester. In the thrust equation, we have two terms. The first term is related to inlet and exit velocity difference. It's related to that times mass flow rate. But we do have a second term. The second term in the thrust equation for a propulsion system is related to exit area times exit pressure minus atmospheric pressure difference. That difference may, in some certain situations, may be reducing your, may contribute towards reduction in your thrust levels. So generally, when we are designing propulsion systems, maybe not for space launch applications, because that's not our main concern, that begins and ends in 8 minutes when from sea level to space. But during, let's say, more sustained flight conditions, long range flight conditions, horizontal flight conditions, we try to design our engines such that we keep exit pressures equal to the atmospheric pressure, at least in the design condition, meaning for whatever altitude we are designing the aircraft for. Okay.
Thanks, sir.
Okay. If you have another questions, we can continue tomorrow. We will have another hour tomorrow. So let's stop here, and let's stop the recording here as well.